All right, moving on. Let's look at problem number 14 here in our review. In this one, we're given the ordered pairs for the initial and terminal points of each vector. It asks us, are these two vectors equivalent? Prove the answer and show your work. Now remember, vectors made up of two quantities, right? We've got a magnitude, right, and we've got direction. So with that, we got to prove that both are equal. So we got a directed line segment, right, with these two vectors. So we got to show their direction is the same, and we're going to have to show their magnitude, which is their length, that they're the same in order to be equivalent. So again, same magnitude, we'll write that down, right, and same direction. So we're looking to prove. So they're equivalent. So again, let's see if that's true. So let's draw a picture just to see these two vectors, all right, to look at it. So let's go ahead and draw in a picture what we have here on these two vectors. So vector QR, we got a starting point of 1, 1, and we got an ending point of 5, negative 3. So we'll go ahead and plot those 2 points, 1, 1. So there's vector QR. So there's this directed line segment. All right, now let's take a look at our next vector, which is vector AB. Now, vector AB has a starting point of negative 5, 0. Here's negative 5, 0. There's A. And then B is negative 1, negative 4. Down here in this quadrant, there's negative 1, negative 4. Here's B. There's this directed line segment. So we're going to prove they're equivalent. So again, vector QR, right? And let's write that in here. And we got vector AB over here. So let's go ahead and find the magnitudes first. So let's get our magnitude, which is our length. So what's the magnitude? So magnitude of vector QR, right, that's it equal to. Now to get that, right, we're looking at the square root, the change in x squared, right, plus change in y squared, right? We know our distance formula. So change in the x coordinates, so we got x coordinates of 5 and 1, right, our horizontal distance squared, plus the change in the y coordinates, negative 3 minus 1 squared. As we look at, again, this is our distance formula. Right, and you can prove that formula, right, if we need to, using the Pythagorean theorem. That's where it comes from. So we got the square root of 4 squared plus negative 4 squared. So we simplify down. And with that, we're looking at the square root of 16 plus 16, which is the square root of 32. So there's this magnitude, and if you wanted to rationalize that, you could. That's 4 square roots of 2, right? If we were to simplify down. Again, that's the square root of 16 times 2, which is 4 square roots of 2. We'll go ahead and rationalize. So there's our magnitude there. So QR, there's a magnitude of 4 square roots of 2. All right, now let's do the same thing with AB. So how about vector AB? What does it have? So let's go to vector AB, and as we look at the magnitude of vector AB, it's equal to the square root. Changing the x coordinates, we got negative 1 and negative 5, plus the change in the y coordinates, negative 4 minus 0 squared. As we simplify, that's what? Negative 1 plus 4 squared plus 4 minus 0, negative 4 minus 0, which is negative 4. And you can see we get what? What's negative 1? And this is a plus 5. Somebody correct my arithmetic here. And this was a plus 5, 2 negatives. But you can see as we simplify down, we got the square root of 4 squared plus negative 4 squared, the exact same thing we had in our previous, right, vector. So it's square root of 32, which again rationalizes to 4 squared is 2, square root of 16 equals 4. So it has the same magnitude. So the magnitudes are the same, right? So the magnitude of vector QR and the magnitude of AB. So same magnitude, check. About direction. So let's find direction. So with direction, right, we could look at the slope. Right, let's find the slope of these lines. So slope, right, our rise over our run. Right? So we look at vector QR. So QR, as we look at our vector together, right, its slope is equal to our rise. As we go down here, we can draw it in here. We're going what? Down 4 units. Right, we're going down from 1 to -3 on the y-axis. So again, a distance of -4. And we're going right from 1 to 5, a distance of 4 units. So we went down 4, rise factor, right 4. Right? We look at our slope, it's -1. And same thing happens as you look at vector AB, what happens? So in vector AB, we want to find its slope. It's equal to what? Down 4. As we look here, we're going from 0 down to -4. And we're going right, what? -5, -1. We're going right 4 units. So it's -4 over 4, or -1. So the slopes are equal. So same magnitude, same direction. So yes, these are equivalent vectors. So that implies these two vectors are equal to each other. They have the same magnitude and they have the same direction. All right, let's show in what we have here with our next example in 15. So in 15, let's draw a picture of what we have in front of us. So vector AB, I've got a starting point of -5, -5. Here's the initial point of A. And B is -1, -3. So down here, right, -1, -3. Here's B. There's that directed line segment. There's vector AB, right, as we're looking at it. And let's go ahead and draw in vector IJ. So IJ, we're going right 2, down 2. And let's go ahead and move this point out of the way. So again, that's -1, -3. Now again, with vector AJ, let's put it in a different color. So IJ, we got a starting point of 2, 2, right 2, right up 2. Up here. Here's I. There's 2, 2. And then right 4, up 3. Right 4, up 3. Here's 4, 3. Here's J. Here's this directed line segment. So are they equivalent? So again, magnitude. Again, what we're looking for. Same magnitude, right? And same direction. If they're going to be equal. That's our question. Right? Is that true in this example? So as we look at finding our magnitudes, so let's start with vector IJ. What's the magnitude of it? That's square root, changing the x-coordinates. We got 4 minus 2 squared, plus the change in the y-coordinates. We got 3 minus 2 squared, which is equal to the square root of 2 squared plus 1 squared, which is equal to the square root of what? 5. So vector IJ, right, we found its magnitude here. Its magnitude, its length square root of 5 units. And how about our next vector? So we look at our vector here. So we go to vector AB. Do it. What's the magnitude of vector AB? The square root, changing the x-coordinates. We got -1. Right, minus the x-coordinate, which is -5 squared, plus the change in the y-coordinates, which is -3 minus -5 squared. And we simplify -1 minus -5, that's -1 plus 5 squared, plus -3 minus -5, that's plus 5 squared. So we simplify, we got the square root of 4 squared plus 2 squared, which is the square root of 16 plus 4, which is the square root of 20. So again, they're not equal. So the magnitude, right, of vector IJ, right, is not equal to the magnitude of vector AB. They're different lengths, so they are not, right, equivalent. to each other. They don't even have the same length. Right? So again, we need the same length and, of course, same direction, which again does not hold true with these examples. All right, so again, let's go to some more examples of vectors, which we'll look at in our next problem.